Okay, good. Well, I'm not piling on. We decided last day. We didn't decide last day. Oh, do I have a? Let me just make sure. I think that's something else, but quiz number 1. What's that noise? Is it on? Is it me? There's like a. Yeah. The air. I know, but the air is loud in this building, especially. Quiz 1 is on Tuesday. Yeah, exactly. My thoughts exactly. On Tuesday, which is January 28th. I guess I had picked it already, but well, this year probably. So yeah, I was looking at, oh yeah, and then on Tuesday, oh no, we're gonna have a quiz on Tuesday because I want to line it up with the application section, which is just kind of playing around with Excel again. And so we'll do the quiz in the first part and then do the Excel playing around with stuff afterwards, which means, of course, the Excel part of this chapter is not on the quiz. In general, I don't want to quiz you on Excel things, okay, so it'll just be on paper. And then I was thinking about it, and it sounds like you guys are pretty swamped generally. So for the quiz questions, to make it a little bit more reasonable, where is it? I was thinking we could just do questions from the textbook. I'll just pull an assortment of questions out of the textbook. And now you're thinking, wait, what? There's a textbook? I know. I am following it pretty closely because that's how I like to do things. Okay, and so at the end of each section, there are answers to the odd numbered exercises. Oh, the tutorials are harder. Yeah, harder. But these are just theory questions. Okay, so for the first quiz, since I just cooked this up as kind of a reasonable solution for quiz 1, let's try it, and I will pull from the odd numbered exercises. Okay, and so you've got the solutions, so you can try those odd numbered exercises. Some of them are better than others, but that's for me to decide, not you. Okay, and so I reserve the right to change some numbers, but for example, if I was to do this one, right, it would say data were collected on lifespans in years and gestation lengths in days for, maybe I change the sample size. Right? Maybe it's not 62 anymore. Maybe it's 67 or something crazy. Right? And then I show you the scatter plot, and you have to tell me what type of an association is there between these two variables, right? And so on and so forth. So I'll be pulling from the odd numbered exercises from chapters 1, 2, 3 was the applications one, so I don't think so. 4 and 5 for the quiz. So will be pulled from, see my own shadow, will be pulled from odd exercises, chapters 1, 2, 4, and 5. Chapter 5, which is what we're doing today. Woof, I know. Okay. How does that sound? Sounds like work, but with a purpose. Okay, we got to do these quizzes. The quizzes are only 10% of your grade. And so because I'm pulling from the odd exercises, I'm not going to give you a practice because, well, it's not worth very much, but also you have the practice, right? All the odd exercises. Okay. And so there, that's your practice for the quiz. How about that? All right. Any questions before we start chapter 5? No. Oh, I left you with a question, didn't I? A little bit of review. I'll bump these down here. I know I left you with a question. We talked about categorical data. I said try for Thursday. And here we are. Time flies. It really does. Copy. I'm gonna close this. So for categorical data, we could have something like this. We talked about how do we summarize one categorical variable, right? We can make a table, or we can make a bar graph, right? So we make a numerical summary and a visual summary, okay? And we're going to keep doing that for numerical data today. But here we've got two variables. Oops, I need my pointer. We've got the shipping, the preferred shipping carrier, and the age group that we're talking about. So a local news survey asked 500 randomly sampled Los Angeles residents which shipping carrier they prefer to use for shipping holiday gifts. The bar plots below show the distribution of responses by age group as well as the distribution of responses by shipping method. Okay, so this is showing the same information, just two different ways of displaying it. Okay, so the first one has information on which shipping carrier, and then we've got it broken up by the ages of the person shipping things, I guess. Okay. And whereas this one has it broken up by the age groups, right? Same age groups and same shipping methods, but now we've got it broken up by the shipping methods. So depending on what you want to communicate, right, that would determine which graph to use. So as a little bit of practice, and I will say there's no wrong answer here. It's kind of a better answer for each of these. But you could use either of these graphs for either of these questions. So part A, which graph, the top or the bottom, would you use to understand the shipping choices of people of different ages? So if you want to understand the shipping choices of people of different ages, like I said, you could use either of these. Okay. I think for me, I would prefer to use this one, right? If I want to talk about the 18 to 34-year-olds versus the 35 to 54-year-olds, it's easier for me to compare them across like this, right? And so you could have done that, right, by comparing all the pink bars, the red bars, and the blue bars. That's fine, right? But for me, it would be easier to talk about and reference the second or the bottom graph. Okay? And so, because then I can compare the bands, right, for the shipping method. So here, I would choose the bottom graph, right? Top or bottom. I would use the bottom graph because then I can easily compare each of the shipping methods within each age group. Or how do I say that? It says explain because it does what I want it to do, is what I want to say. That doesn't help. I would use the bottom because it is easier. Still pretty stupid to say, because it's easier to compare ages, to compare across ages. Like I said, they're showing the same information, so it doesn't really matter, right? But this is where you want to think about, okay, well, what am I trying to communicate, right? What's the best way to communicate whatever I'm trying to get at? The next one, which graph, top or bottom, would you use to understand the age distribution across different types of shipping choices? Well, that one's kind of the reverse. So of course I would use the top. Right? Oops. Because if I want to figure out, okay, across the different types of shipping choices, then maybe I want to stack those shipping choices and I will want to look at the age distributions within each of those shipping choices. I'm just going to say top. A new shipping company would like to market to people over the age of 55. Who will be the biggest competitor? I want you to think about which of these graphs you would use or more easily use, right? So imagine you've generated both of these graphs and your client has asked you, okay, I want to market to people over the age of 55. Who's my biggest competitor, right? And then, so think about which of these you would use. I think the bottom graph is probably the easiest one to use in this case, right? Because otherwise you get the same information, right? The 55 plus here, right? But then you're overinflating the not sures, right? Whereas if we look in the age group, right, then the not sures are actually kind of a small proportion, right, of the 55 pluses. So in the 55 plus group, who's your biggest competitor? USPS. Oops. And my explanation will be this graph. What if FedEx would like to reach out to grow their market share so as to balance the age demographics of FedEx users? Then to what group should FedEx market? So now, within FedEx, right, then I'm going to be looking at this top graph. And if they want to balance their groups, right, this pink band and the red bands are fairly similar, but they would want more of the blue bands, which is the 55 plus. '55 plus group. Okay. Good. Take some practice. And like I said, you can answer these questions, but some of them, one of the graphs makes it easier than the other one, right? Okay. Any questions before we start chapter 5? No. Okay. Chapter 5. We're now exploring numerical data. Numerical data, we have lots more that we are able to do with numerical data, right? And so last day we introduced a data set on the loans data set, and we talked about the different variables. And one of those numerical variables that we have is the interest rate, right? We can also talk about the loan amounts, right? But we've got a couple of numerical variables to work with. And so we'll be exploring those today. And so this is going to involve first a visual summary, followed by a numerical summary. That's what we did for categorical data, right? We made bar plots, or we can summarize them in a table. That would be considered a numerical summary, right? And so we're going to do the same thing for numerical data, right? One of the first things that you want to do if you have a numerical variable is look at the distribution. So given a numerical variable, the first thing we do is look at the distribution of the data. Okay. There are some kind of key ways to do that. So look means to visualize. And usually what we do is we visualize with a histogram. Okay. And so often a histogram. A histogram looks like this little guy. Okay. But we've got some other options that I want to outline. Can I just write here? A histogram looks like this. I'll bump this down. Think. This looks like a bar plot, and it is, right? But what's happened? Your numerical variable has been put into bins. So we call these bins. So this is a bin. So your numerical variable has been placed into bins. The data is placed in bins, which I think of kind of as temporary categorical variables, right? But then because we're working with a numerical variable, it's on this continuous scale. And so we've got the interest rate down here on the x-axis, right? But the height of each bin shows the count in each bin. So we've got these interest rates, and a little bit harder than categorical variables to talk about the distribution here. If you had to describe this distribution, right, that's not the easiest thing to do. And so we need some new shapes. So just like if I asked you what shape is this, or what shape is this, or what shape is this, you know all those shapes, right? Back to basics. How about we add some new shapes? How about we add something that looks like this. Or how about we add a shape that looks like this? That's handy in this case. Or how about we add a shape that looks like this? Are they watching a movie?
Yeah, it sounds like
Rude. Well, I don't have any movies. I should find some movies. I don't know. Let's give these guys some names. I can't beat a movie. I can't be more entertaining than a movie. We're going to call this, I'm just going to jump right into it and call it the normal distribution. Okay. And so usually we spend a little bit of time kind of developing it. Let me make it more obvious. This is a bell-shaped, if you prefer to start off with, right? Some shapes that we know. Okay, but we're going to call it a normal distribution or an approximately normal distribution. These two are skewed distributions, but they're skewed in different directions. Okay, and so the key thing to remember is that they're skewed in the direction of the tail, which can feel a little bit counterintuitive, just because usually we want to talk about, okay, where is the lump of the data? But in statistics and data science, we want to talk about these extreme values, right? Oh, we've got these extreme values over here. So this first one skewed to the right, or a positive skew, if you prefer. And this one is skewed, oops, I'll clean that up. Skewed left, or a negative skew. Left skewed, right skewed. Or a normal distribution. If you had to apply a shape to this thing, then you want to think broad strokes, right? And so this is from a sample, right? But it's coming from a bigger population, right? So the population would presumably follow roughly the same shape, but not exactly the same shape. So you want to think about kind of broad strokes here like this. Doesn't lift off. I was pretty pleased with my first part there, but like that. So if I had to describe this distribution, I would say it's skewed to the right. Which means that we have many of the data points kind of over to the left, but then we've got some very large data points. Yeah. So histograms are the thing that we're going to use the most to look at the distribution of a numerical variable. We've got some other options. Let's see here. How about I copy and let's just focus on this little guy for now. This is the same data as the histogram. Okay. This is called a dot plot. Okay. I don't want you using dot plots, but I want you to see dot plots. What's the benefit of the dot plot versus the histogram? The only benefit is that you can see each individual data point. okay? Versus the histogram, they've all been put into bins, and depending on the bin width, it can tell you more or less about the distribution. And in Excel, you'll be able to change the bin width, but I usually recommend just using the default. It does some stuff for you in the background. And so usually I just keep the given bin width, but you can adjust it. Okay? Which would do what? If you made this bin width smaller, right? You'd get tighter bars, and eventually your bars would end up looking like this dot plot, right? Because that's all the bars are in the histogram, is just each observation stacked on top of each other in each bin, right? So the dot plot still shows the distribution. So the dot plot shows the same distribution, right? It's a little bit busy, even with this few data points, right? And so if you have a lot of data points, it would get really, really busy. And so and shows each individual data point. Okay. So if that's something that you're looking for, then the dot plot is probably the way to go. But usually, right, we use a histogram. We usually prefer a histogram. It's my job to give you options. Right. And then limit them immediately. Let's do. Now it sounds like there's a movie on this side. Is there a movie on both sides? Unbelievable. Another option that we have is called the box plot. So named because, well, there's a box. So that's kind of a dead giveaway. But what does it do? The box plot communicates slightly different information than the histogram. If you had to take a guess at what this thing looks like, or what this distribution is telling you, what's the most kind of jarring thing that we see? These guys. Okay. So the benefit of the box plot is it highlights any outliers. Okay. Outliers are extreme values in our data that we should probably investigate or that we're interested in, right? And so a benefit of the box plot is that it highlights outliers. And I will throw in here for good measure, usually using the 1.5 IQR rule. Don't worry, just write it down. Usually using the 1.5 IQR rule. That piqued your interest, I can tell. Or maybe not. Okay. So what the box plot does is it splits your data into quarters. Okay. And so the box plot splits the data into quarters. Okay. If you've got your number line down here, 0% interest rate, 10% interest rate, 20%, 30%. Okay. Then what's going on here is this value here would be the minimum, right? Your smallest data point. And these very kind of cutely are called whiskers. So sometimes we call it a box and whisker plot. And I didn't know this until I was reading the textbook. I always thought that John Tukey, who's a famous statistician, invented the box plot, but I guess it was someone else who invented it, and he just called it the box and whisker plot. So now I can't remember who that someone else was, but it's in the textbook. Kind of a fun fact. So I always have said that it's John Tukey, but it was not. He just renamed it. Yeah. Doesn't matter. So these are called whiskers, kind of cute. And how the whiskers work is, okay, so we start at this minimum, okay? And then they extend to, if you're splitting your data into quarters, then what's a reasonable name for the next stop? Well, how about quartile 1? So this value here is quartile 1 or Q1. Which means that in this distance here, we have 25% of our data, right? So you've sorted your data, your interest rates from smallest to largest, and now you're just chopping it up into quarters, right? Kind of breakpoints. So that means you have 25% of your data in that distance. Okay. If we compare the distances here, right? This is going to be another 25% and another 25%. Okay. Then a shorter distance means what? Means it took a shorter distance to move that far through 25% of your data. And then if you've got a longer distance, then it took you longer to cover the same amount of data, right? 25% of your data. Okay. And so these longer distances actually show that there's less data in that span. Okay. That's hard for our brains to do, right? But if we compare it to the histogram, that's what we see, right? We see a ton of information here. A lot of these points, right? These are counts. And so a lot of these points are happening up until maybe this point here, right? The first quartile, second quartile, and then it takes us longer to get to the third quartile. Okay, so I didn't give myself enough room. I know. And over here. This is your second quartile. But your second quartile is if you're 2 quarters through your data, you're halfway through, right? And so we give it a special name. You can call it Q2 if you want. But Q2 is also called the median. So the median is the point, the data point that splits your data in half. The median is the data point that splits your data in half. Right, 50% below it, 50% above it. Right, so all of these require you to sort your data. Now we're not going to do it by hand because there's kind of some finicky things that you need to do if you're doing it by hand. I usually use my my patent pending. No, there's no patent pending. Boop, boop, boop method. Right, I just sort my data manually and then I boop, 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 boop my way in. Boop, boop, boop. It's the easiest way to do it. Or you can use Excel. Excel does apply some fancy kind of weighting mechanisms. And so sometimes they won't match what you're doing by hand. But like I said, I'm not going to get you to do it by hand. So you're okay. Right. What I need you to know, though, is that the median splits your data in half. Right. Okay. Can you guess? Well, your third quartile is this little guy. Then we've got some activity up here that I'm holding off on for just a little bit. So if we look at this box, the distance between Q1 and Q3 is called the interquartile range. So the inter means between, right? Interquartile range is called the IQR. And it's going to be the distance between Q1 and Q3. Which means that the easiest way, you could take the absolute value, but the easiest way to calculate these is the interquartile range is Q3 minus Q1, right? Because you place them on a number scale and they're increasing. And so Q3 is always bigger than Q1. Okay. So in this case, if we had to guess, right, here's 10 and here's 20. Hard to say from the box plot, but I would put this around, I don't know, 13, right? Not quite 15, maybe 14. And put this around, I don't know, 8. So for example, our interquartile range might be, if this is at 14, and this is at 8. Six. Math. So my interquartile range, if those are the numbers, would be 6. Now, the most kind of common rule that we use to determine if we have outliers is we take 1.5 times this distance, right, times the interquartile range, and we can move down from Q1 that far, and we can move up from Q3. Okay. And so now we've got these kind of fences or bounds. Anything beyond these values are considered outliers. Okay. So to determine if there are any outliers, you guys read the book Outliers by Malcolm Gladwell? Same. Malcolm Gladwell does a lot of kind of stats for fun books. And so Outliers is one of them, which is pretty interesting. So if you've got some spare time, you can read Outliers. I know. You're not reading for fun for a while, are you? Cute to think though, right? You've got a tea, you're curled up with a book. And not just a textbook. We use the 1.5 IQR rule, okay, which says that, okay, we're gonna have a lower bound on the lower end, of course. So what we said was, okay, we're gonna take this 6 times it by 1.5, okay, which is what, 9, right? So then I'm allowed to move down from Q1, I'm allowed to move down 9 units. Anything after that is considered an outlier. Okay. Here from, let's say 8, I would have an interest rate, anything after -1 in this case, if I have my numbers, right? If we use these numbers, that would be considered an outlier. That's not gonna happen, right? Interest rates are positive, otherwise they'd be paying you, right? That sounds nice, but not how it works, right? So we're not gonna have any outliers on the lower end, okay? But the lower bound is gonna be Q1 minus 1.5 times the interquartile range, which for our example is 8 minus 1.5 times 6, which means 8 minus, if I did it right, minus 9 is -1. Right? Therefore, any interest rates below -1 would be considered outliers. Would be considered outliers. It's nice to have these rules because when you're looking at the data, sometimes you suspect you have outliers, right? I suspect there are outliers on the upper end, okay? But it's nice to have, there are outliers on the upper end because they're bigger than this value. Okay? And so for the upper bound, we do the same thing. But we move up from Q3, right? So we take this distance, right, the interquartile range, we multiply by 1.5, and there's lots of different ways, right? You could do 2, you could do 3, that's crazy. 2.75, why not? PhDs have been cranked out, probably, from these different values, but 1.5 is the one that we use, right? There's no reason, but it's kind of the settled on reason, or the settled on distance. So from Q3, I'm allowed to move up 1.5 times the interquartile range before it's considered an outlier. Okay. And so here, from Q3, I'm allowed to move up 1.5 times the interquartile range, which for us, if we have 14 is our Q3 plus 1.5 times 6, 14 plus 9 is 23. Is it? Sold. So now if we go here, I'm playing fast and loose here. It's not technically going to be at 23 that this whisker goes to. So this whisker, oops, there. This whisker is technically going to go to the largest data point inside 23. Okay. And so maybe I shouldn't be so so lackadaisical about it, maybe I should put 23 here. Just to highlight that, okay, your box plot only shows your data, right? We're finding bounds and we're finding, okay, because you're past this limit, then I consider you outliers, right? But we're not adding to our data set, right? And so that's why usually we find this bound and we draw our whisker to the smallest value inside 23. Yeah? We see that there are two values that are larger than 23, which means we have two outliers in this case. There are two interest rates larger than 23, which are considered outliers. And I'll put in brackets, right? Indicated by dots or stars or whatever your software uses. Indicated by dots or stars or some other, sometimes pluses, doesn't matter. You'll see. Right. The whole point of visualizing data is to just quickly be able to gather information, right? And so box plots are good for figuring out, okay, I suspect there are outliers, right? If I go back to this histogram, I suspect that these guys might be a little bit too far from the rest of the data, and I might call them outliers, especially if there was a space and then another one, right? Then I would suspect they're outliers, but you would confirm it using a box plot. Okay.
So on our box plot, Q4 would end at the very last data point.
Yeah, so then,
Represents our,
yeah, your maximum, let's see here. Your maximum is your Q4. Nice. This is also called a 5-number summary. That's just a numerical summary of a box plot, right? You've got your minimum, you've got your Q1, you've got your median, you've got your Q3, and you've got your maximum, right? So that's called a 5-number summary. A 5-number summary is a numerical summary, but it doesn't give you the outliers, but it is a numerical summary of a box plot. The minimum, Q1, the median, Q3, and the maximum. Even without indicating if there are any outliers, right? You could find the interquartile range, and you could check if your maximums and your minimums are inside or outside the bounds, right? You don't know how many outliers, but we can still determine if there are outliers. By calculating the upper and the lower bounds, by calculating I'll say the lower and the upper bounds. And comparing it to the minimum and the maximum. And comparing to the minimum and the maximum. right, respectively, I'll say. It won't tell you how many outliers, but it'll tell you if there are outliers. Won't tell you how many outliers. But if there are outliers. We care about outliers just because they're the ones that we want to analyze, right? And so kind of the first step is to figure out, well, are there any outliers, right? And then you want to explore, well, is it just a typo, or is this actually an outlying observation that I want to analyze, right? Okay. Good. Acres of time. I say that now, but like I said, yeah.
So with these Q1 and Q3 are always like the corners of the boxes that this alignment is under.
Yeah. Nope, that's it. That's the box plot. And that's the box. Is always from Q1 to Q3. And I think Excel uses, well, I know Excel uses the 1.5 IQR rule, so that's kind of broad strokes. I think you can probably change it, but I don't know how. And I don't need to know why or how. You don't either. Okay. No, that's what I was wondering. If this is all you had, you could figure out what the distribution looks like, right? In terms of the shape, right? And the shape is going to kind of guide our analyses. And so that's why it's so important to talk about the shape. Okay, so here we could use the box plot to determine the shape. Can I sit down? Are you guys okay with that? I'm like, it feels like cheating in a way.
We're all sitting down.
I know, but you're learning. I'm just blabbing, dancing around up here. Okay. That's better. Thanks. I can still see you guys. That's nice. Hey. We could use the box plot to determine the shape. But a histogram makes it easier. For example, if I have maybe a box plot that looks like this. Let's start with one that we've seen before, right? Kind of similar to what we had in the generated one. Now I've made a shoddy one. No outliers this time. Okay. That's okay. Like we said, these shorter distances cover more data, right? Or the same amount of data. So 25% of your data here, 25% here, 22%, 25% here, and then a final 25% there. If you had to translate this into a histogram, right? As we saw, that might look something like this. Yeah. Whereas if we had a box plot that maybe looks like this, you had to think about the shape of this distribution, I would say it's approximately normal, right? It takes a long time and then we've covered 25% and then do. Something like this. I should, for what I'm about to say next, should line those up. Right? So now, this is the median. That's the center. Okay. This on your normal distribution, right? Kind of applying that name that we just learned. The center is at the mean. I'll write that. But for a normal distribution, the mean is going to be the same as the median, or roughly the same as the median. The mean is what? The mean is the average. Whereas if we go back to up here, what happens to the average if you have outliers? You kind of jot down a quick little data set and you know how to take the average of maybe 4 things. Now change one of those the biggest thing to 100 times that. Right? Exactly. So the mean is going to be pulled in the direction of the tail. Is pulled, I'll say, towards outliers or the tail. Okay. Whereas the median, and I should have lined these up better. Let's do this. Line it up with the median on the box plot above. The median is going to be a better measure of center than the mean would be in this case, because the mean might be pulled kind of out here or something. So the mean is always going to be pulled in the direction of the outliers. It's not until we have a symmetric distribution that the mean and the median are roughly the same. So, okay, it sounds to me like the median is a better measure of center, okay, which is one of the things that we're going to be interested in. The problem is we have a lot more tools available to us in terms of analytics for the mean. We don't usually analyze the median so much, okay? But we do say that the median is a more robust measure of center than the mean. Measure of center than the mean. I capitalized median, but let's capitalize the mean too. So it's a better measure of center if we have skewed data, right? And so making it, I shouldn't say it, making the median a better measure of center for skewed data. So if you have skewed data, some common skewed data, as soon as it involves money, usually it's skewed. And unfortunately, it's skewed to the right. which means most of us are kind of down with the lumps. And then over here, we've got these kind of extreme values. Okay, and so money variables are often skewed. And often they're skewed like this, right? For income, for example, right? A lot of us, it's about the same. Income, for example, right? Money variables. Most of us are kind of down here. And then there's very few that are up here. Right?
It's just because they're so smart, right? They deserve it.
Yeah, they work hard. Yeah. It's not like money begets money or anything, but
This is a stats course.
yeah. So money variables is kind of the most common error that I hear and read about in terms of stats, right? And so on the radio, right, average house prices. Should we be talking about average house prices? No, right? Because house prices look like this, right? A lot of homes are kind of here with a few that are being sold for, or I guess marketed for for huge amounts. And so, right, then the average is not a good measure of center, right? Then we should be talking about the median. So now you can pay attention to all these kind of quick little snippets they play on the radio and stuff. Maybe people don't listen to the radio anymore. That's how they get away with it. Right, but you'll see little news articles and things like that where they are clearly talking about skewed distributions, but they're using the mean when we should be using the median as kind of indicative of the center. Okay. So knowing the shape determines which measure of center we should have. Okay. And so the shape of a distribution determines the appropriate measure of center. Oops. Measure of center. And we haven't talked about the spread yet, but the spread is also a component. Right? So measure of center and spread and spread. So if we have a normal distribution, which we know is kind of a bell-shaped, that's really annoying. A normal distribution is a bell-shaped unimodal. Mode means peaks, right? Mathematically, it means the most frequently occurring value, but for us, it's going to be the peak of the data. Okay. I'll write that down after this, but a normal distribution versus, let's lump the skewed distributions into a non-normal distribution. So any non-normal distribution yeah. I still can't tell if it's from here or from there. It's like bouncing off of this wall. Yikes. So for a normal distribution, we use the mean because it's more powerful. We can use the median, but there's not a lot. It kind of ends at the median as a measure of center. And so for us, we prefer to use the mean if we can, right? And so we could, or the median if you want, but the mean is going to be more powerful, okay? For a non-normal distribution, right, as a measure of center, we should be using the median, right? The problem is we're able to calculate the average, of course, right? We're always able to calculate the mean, the median, all the spreads, right? It's our job to know which one applies to which shape, okay? And so we could calculate the mean, but we're not going to, right? Because you know better. So if I told you that, just to lead us into why we care about the spread, if I told you that I found a mosquito that was 1 centimeter bigger than the average, you would say what now? Why? Because you know mosquitoes, well, you know the average mosquito, right? But you also know the spread around those mosquitoes is very, very small, right? And so that led you to this gut reaction of, what? 1 centimeter larger than average, right? Whereas what if I said, I found a dog, and you won't believe this, it's 1 centimeter longer than the average dog. You'd say, okay, why? Because that spread is huge, right? We understand, we have this intuitive spread, right? And so one of the ways that we're going to analyze if something is kind of extreme or not is how far is it from the center, right? But also incorporating the spread. Okay? And so the spread is kind of our next stop. Okay? And for us, if we have a normal distribution, we're going to use the standard deviation. The standard deviation is a measure of spread, okay? And it's the measure of spread that we use if you have a normal distribution. Okay? Whereas for a non-normal distribution, we would use the interquartile range, which we've already seen. Is there some, sorry.
Oh, you're good.
I couldn't see. Hiding from the window. So for non-normal distributions, we use the interquartile range, and that's a good measure of spread, right? Kind of the distance between the middle 50% of your data, right? That's a good measure of spread. So the standard deviation, and you know, we could go through and calculate it by hand, but oh, gross. But the standard deviation is denoted by a lowercase s usually. Okay. Is denoted by a lowercase s for the sample standard deviation. Okay. So if you've collected data and you're calculating the standard deviation, this is the sample standard deviation. Sample standard deviation. I'll give you the formula, but of course we're just going to use Excel, or I'll give you the standard deviation, so I don't need you to be able to calculate it. But it goes a little something like this. From each xi, so from each data point, I'm going to subtract the mean. Right? That's a good measure of spread. How far is each of these things from the mean? Okay, just how the mean works though, if I was to add these all up, they would add to 0 just as a fact, right? How the mean works. And so to get around that, right, because I'd have some values below the mean, some above the mean, right? And so to get around that, we square each of these deviations. Okay? And then we add these all up. Right? So from each data point, right, in your data set, you would subtract the mean, right? Find how far from the mean is it. Then you would square each of those values. And then you add all those up. But wait, there's more. Then we divide by n minus 1. There's a lot of theory why it should be n minus 1, but for us, it just gives us a better estimate for the spread than just n does, right? If we kind of think about the average, right? You add up all your things and you divide by n, right? I'm assuming you know how to take the average of something, right? And so then, right, your average is the sum of all the things divided by n. And so dividing by n minus 1 feels a little bit wonky, but it's okay. It just gives us a better estimate. Okay. And then the standard deviation is going to be the square root of this thing. But at its core, it's looking at the distances from the mean, right? Which makes sense, right? Hopefully. And that does some things, right? And so before we took the square root, this is what's called the variance. And so the variance is the standard deviation squared, which would take away that square root. The problem with the variance is that the units are squared. Okay. So usually in an introductory course like this, that's harder to think about and talk about. And so that's why we use the standard deviation. But if you keep going with stats, then you might find yourself using the variance, right? And so I'm curious, because I know you've done some standard deviation work. Yeah, for your confidence intervals, you need to know the spread, right? But you probably use the standard deviation and not the variance. Right? Okay, so here, just a quick note, the units would be squared for the variance, which is why we usually use the standard deviation instead. Standard deviation. Yeah. Yeah. Yeah, we're not going to do it by hand, but what Excel does is this for the standard deviation, and then just doesn't take the square root for the variance. Equals variance. Yeah, in Excel, we're going to use, I think it's stdev.s, right? Of all your values, right? You want to use the .s because it's a sample standard deviation, right? So you'll always have a sample. In fact, any data that you've collected, unless I tell you, assume this is the population, which is pretty rare. But then you'll have a sample standard deviation, which means that we're going to divide by n minus 1, which is not in our class. So this is for the sample standard deviation. Right, so that's the one I want you to use. Okay, so it's kind of hurting me a little bit to not go through the formula, But there it is. I did it. We talked about it, but you're going to use Excel, or I'll give you the standard deviation, right? The standard deviation is this. Yeah. So if we have a population that we've sampled from, right, there is also a population standard deviation, right? We said this is the sample standard deviation, which means that there's going to be a big brother kind of corresponding measurement that we don't know about, right? And so in terms of our notation, for the mean, let's see here. For the mean and the standard deviation, oops, let's do the variance too. And the variance. We're going to have sample information, but we're also going to have population information. So yeah, it's nice because it gives me kind of a first, is to go to a different class. So gives me an idea of how much time I have left. So we're going to need notation for if the mean is from the sample, right? Or if the mean is from the population. Okay? And so if the mean is from the sample, we're going to use, generically, we use X bar. So X with a bar over it. Anything with a bar over it is an average, a sample average. Okay? Which makes this your average smiley face. Anything with a bar over it, right? Sometimes we use kind of variable names, like if we're using the interest rate, you might have interest with a bar over it, right? Just to indicate that that's the sample average interest rate. Okay. But X is what we use as a placeholder for the name of your numerical variable. Okay. And we already introduced the standard deviation. We use a lowercase s. And then we said the variance is the standard deviation squared. And so makes sense to use s squared to denote the variance. Okay. So that's all the things that we can calculate from our sample, right? Anything you've calculated uses one of these letters. Okay? For the population, we tend to use Greek letters, okay? Just to kind of separate them and say, okay, these are parameters, okay? Population parameters. And so for the mean, the population mean, we use a mu, which you pronounce, or if you had to write it out, you would write mu, mu. Greek letter mu. It's like a fancy M. How about the standard deviation? Lowercase sigma. Nice. You've seen that before. I wonder if maybe you had sigma in your formulas for chemistry. Sometimes we get a little bit sloppy with the notation, and sometimes we use sigma instead of s just to highlight that it's the standard deviation. Okay, so but it should be s, but it's okay. And then the variance is sigma squared. Measurements from the population, we call them parameters. And so parameters Notice the P and the P. Parameters are measurements from the population. Whereas a statistic is a measure from the sample. Ah. Notice the S and the S. Statistics are measurements from the sample. Right, so statistics as a field. Oh, sorry. You almost missed the best part. So statistics as a field is where we analyze measurements from a sample, right? And so, but what are we really trying to do? We're trying to learn about the parameters, right? Their corresponding parameters. And so inference, introducing a term here, a new term, I guess. But inference is when we use statistics to infer something about the population. Inference is using statistics, right? And in this case, I mean measurements from the sample, right? The proper use of statistics, really. But it's also the field of statistics is inference, generically. And so using statistics to infer something about the corresponding parameter. Which means that we use the sample mean to try to infer something. If I say infer, right, we kind of have a sort of an understanding, right, to learn about the population mean, right? I have all the information I could possibly want about my sample. I know exactly what my sample looks like, right? That's not interesting to me. I'm trying to use that sample to learn about what the population looks like, right? And so that's what we're doing here. Broad strokes, but still. Okay, good. To describe a distribution, we need to talk about three things, right? So to describe a distribution, we need to discuss three things. One is the shape, right? We already spent a lot of time on the shape saying, okay, well, in the end, right, the shape of my distribution determines what my appropriate measure of center and spread are going to be, right? And so the shape is kind of your number one. Okay. And the second thing is going to be your center, and the third thing is your spread. Right. A lot of the time we won't have that intuitive knowledge about the spread, like the mosquitoes, right? They're very, very little spread, right? Versus the dogs, we know there's big spread, the lengths of dogs or whatever we're talking about, right? So often we don't have that intuitive knowledge. And so then we need to kind of get an idea of how wide of a range we're expecting our data to have. Okay. And so in terms of the shape, we've seen a normal distribution versus a non-normal distribution. In general, all of these are what we call unimodal distributions. These are both unimodal distributions. Which brings me to the mode. The mode of a distribution. And like I said, in math, the mode is technically the most frequently occurring value. Okay? But for us, because our data points aren't necessarily always, they could all be different if we have a numerical variable, right? And so we don't have a most frequently occurring value. And so for us, the mode is going to be the peaks of our data. Okay, so it's going to be the peaks of our data. So we have a unimodal, right? That means there's one mode. Bless you. Unimodal, it has one mode or peak. Bimodal has two distinct modes, right? So two distinct peaks. Bimodal, two modes or peaks, right? These should be distinct. You don't want to get caught in kind of sample specific information, right? You're going to look at a distribution from a sample, but as long as you remind yourself that, hey, I could collect a completely new sample and it would still be representative of the population if I did it correctly, right? If I sampled randomly. And so, but I know the shape would change slightly, right? So when you're talking about the shape, right, and the modes, broad strokes only, right? She didn't have it in this textbook, but in a different textbook, she talks about having a cooked spaghetti and you kind of plop a cooked spaghetti on top. So it's kind of broad strokes. And so that's what I want you to do. And then after bimodal, we go multimodal. Because at that point, more than two modes. It can include two modes. You can just call it multimodal if you want. But usually if there's two modes, you want to talk about that. To illustrate, hey, had it all queued up. Kind of chose my own adventure here, but oops. Guess I should keep the description. Here are three different, this is a population distribution, but just ignore that, with the same mean. So these all have a mean of 0 and a standard deviation of 1, right? And so knowing that, right, these are all very different, right? So it all comes down to the shape, right? And so here, I would call this, so it's just the blue bars that we're trying to generalize here. Like this. So the shape is the only difference between these, but these all have a mean of 0 and a standard deviation of 1, if you calculated it. So knowing the shape makes a huge difference. Here we would call this bimodal. This is a normal distribution, or unimodal and symmetric. Versus this one is skewed right. Oops. But in terms of modes, it's still unimodal and skewed. What's interesting is, as a general rule, right, especially if you have a normal distribution, then roughly 68% of your data is going to be within one standard deviation of the mean. And so that's what these darker bars are. So here we'd have roughly 68% of your data in this kind of stretch, roughly. If you move out another standard deviation, then within 2 standard deviations of the mean on either end, you've got roughly 95% of your data. That's a lot. And that's one of the reasons that we use 95% confidence intervals, right? And we use 2 standard deviations away as kind of a guide to figure out, okay, these are kind of extreme values, right? Or what I saw is unusual. So as a general rule, roughly 68% of the data, probably should say population here, but for us, let's focus on just the data. 68% of the data is captured within 1 standard deviation of the mean. 95% within 2 standard deviations of the mean. And finally, roughly 99.7% within 3 standard deviations of the mean. This is called the empirical rule. So here, this is called the empirical rule. I should have written that out. Or the 68, 95, 99.7 rule, if you prefer, which I do. I find it's more helpful, right? And so how we are going to use it is that from here, right, anything that's more than 2 standard deviations from the mean, and we can, so the mean is in the center, right? We know that, of a normal distribution. Then I can move out 1 standard deviation. Okay, that's 68%. But then 2 standard deviations, that's covered 95% of the curve, right? And so now anything beyond that, right, that's the leftover 5% split evenly between the tails, right? And so we say, okay, that we're confident that we've captured the true parameter. There, I got ahead of myself. I'll take it back. No, I won't take it back, but I won't write it down. You don't have to know it yet. But this is why we use we use 95% confidence intervals. And any observation beyond 2 standard deviations is considered extreme. and any observation beyond 2 standard deviations is considered extreme. Or unusual. Okay. I did get ahead of myself, but still. Nice to have seen it. So just as a rule of thumb, right? An extreme or unusual observation, right, is going to be more than 2 standard deviations from the mean, which we're going to say, okay, well, that makes it unlikely to have come from that population, right? It probably came from a different population, right? And so that's how we're going to kind of turn it against itself. Okay. Come on. There's some, transforming data. You guys transform data a lot. When you do your log graphs, log, use log paper. I know that, I think.
We did.
You did? Oh, you're over that.
Well, now that we've learned it, like just use a computer application, it spits out your log.
Ah, cool. Well, it's just taking the log anyways. But why would we use the log? So if we have a skewed distribution, for example, this top one here, right? This is only slightly skewed. Okay, this is the percentage of unemployed in some county data set, some US data set. What happens when I take the log and they're using the log base 10 is it becomes more symmetric, right? It's a way of kind of forcing a normal distribution, right? Why would we want that? Because we said, well, the mean is more powerful, but we can only use the mean if we have a normal distribution, right? So one of the reasons that we want to do a transformation is so that we can use the mean on our transform data, right? And so kind of more obvious is if we talk about this population data, right? This is extremely skewed. I think it's within some counties or whatever. But if we take the log of that population, now all of a sudden I have this beautiful normal distribution where I can use the mean as my measure of center. I can use my standard deviation, and I can do all these analyses that we'll have eventually. This whole course is clickbait. Soon you'll know how to do it, right? But we got to build up these skills first. And so here, oops, come on. Transformations. Lop that off. Right here, we've got this broad strokes, remember? Maybe I made it a little too broad. We transform data. If it is skewed. And so the log transformation is a common transformation. There are other transformations that we can do. And so we transform data just in general, if it is skewed, with the goal of kind of creating a normal-ish distribution, or at least a unimodal symmetric distribution. Okay. With the goal of creating a unimodal symmetric, which I'm going to call the normal distribution. It's broader than the normal. The normal is unimodal and symmetric, right? But for us, let's just focus on the normal distribution, where we can use the mean and standard deviation. Some other transformations that we have, we can take the square root, right? If you're not finding what you want with the log, so some common transformations. First one is a log. That can be log base 10 or log base e, which is the natural log. Play around with those. They behave similarly, so it doesn't really matter. You can take the square root. Square root of one or both of your variables. Makes it harder to interpret the results though, right? And so kind of the transformation comes with some baggage. You'd have to interpret your results in terms of the log or kind of unravel it back to the original scale, okay? Or the square root, or the inverse, 1 over x, right? Those are all options, depending on what shape it is you're dealing with, right? For us, you'll be working with logs most of the time. But remembering that the goal is to get this unimodal symmetric distribution so that you can leverage the mean and the standard deviation. Last thing I want to bring up is these mapping data. So if you have geographic information, right, then often mapping it is going to be useful. If you have geographic data, which usually I skip, right? Usually I skip geographic data. We usually don't have a lot of geographic data in an introductory course like this, but I feel like you guys might actually have some geographic data, right? Different parts of the valley, maybe where your measurements came from, right? That kind of thing. And so then mapping the data. So if you have geographic data, mapping it can be useful. And we usually use something like this, which is called a heat map. Doesn't have to be a map, but usually it is, right? Literal map, okay? Where this is for the poverty variable in the United States, okay? And dark blue is a low poverty rate. And then as it gets lighter and lighter and lighter, you get a higher poverty rate, right? And so we see these pockets here where we have a lot of poverty, and we're able to gather that information relatively quickly, right? Instead of maybe looking at a bar chart for each of the counties, barf, right? Then you can gather this information pretty quickly, right? And so that's, if you have mapping data or geographic data, then it's worth considering, okay? And I know what you're wondering, wow, can Excel do that? I don't know. Guess we'll find out. I'll play around with it and see. I don't know. But can do it in R, but I don't know about Excel. Anyways, if you have any questions, let me know. Otherwise, I'll see you for the quiz on Tuesday. Oh, yes. Let's see here. Let me stop this recording first.